Louis assis. C'est toujours les mêmes. Hein? Okay, the first thing is whether you have questions on yesterday's lecture. I went a bit fast on this derivation of the active gel equations. I didn't want to go into the details, but if you have questions, I'm happy to answer either now or after the lecture. No immediate question? Okay, so what I want to do is discuss pneumatic tissues as I started yesterday. And in a pneumatic tissue, there is a pneumatic order parameter. So this is the average of n alpha and beta minus 1/3 in 3 dimensions or 1/2 in 2 dimensions times delta alpha beta, where n is the vector sitting on the cell. One way, as I said, biologically, is to look at the centrosome, which is the point for which the microtubule radiate, look at the nucleus of one cell, you draw a line between these two, and that's the direction of n. So a tissue is pneumatic if this is finite in the absence of stress. Now, why could it be finite in the absence of stress? The first idea is, as for a solution of rods, there could be an isotropic to pneumatic transition if you increase the cell density. So something which is, I would say, Onsager-like in a sense that if you increase the density in a solution of rods, they tend to align, and there is a first-order transition between a disordered system and a solution of parallel rods. So that's one way through which it could become pneumatic. The other way through which it could become pneumatic is that there could be a gradient somewhere that aligns the cell. For instance, in development, you have morphogen gradients. So a morphogen is a small molecule that influences the behavior of the cell. If I call phi the density, local density of morphogen, and if it has a gradient, I can make a tensor with a gradient which is here, and Q alpha beta will be proportional to this tensor. So in this case, I will have Q alpha beta. I have to check, I put it 0, which is proportional to d alpha phi, d beta phi, minus 1/3. Anything you could imagine that allows you to create a tensor could align the cell, and then you can imagine that there is a spontaneous pneumatic order parameter which is proportional to this tensor. The two most classical ones would be a spontaneous pneumatic isotropic phase transition, or some morphogen gradient where the cell will align along the gradient, and if they align along the gradient, this pneumatic tensor will be of this form. So that's an external field if you want. Now, if I add if I put a stress in the tissue, and what I will care about in the following is the traceless part of the stress. So I take out the pressure. So I call it sigma tilde alpha beta. Sigma tilde alpha beta will orient the cells as well. It might orient the cell in a different direction than the spontaneous orientation. So there will be a tilt of the orientation, which depends on the stress. And I will assume that the response is linear. So I'll write that Q alpha beta minus Q alpha beta 0 is proportional to the stress. So it's something like sigma tilde alpha beta over some characteristic stress, sigma 0. One of the things which is not obvious is the sign of this sigma 0. At least I don't have any intuition when sigma 0 should be positive or sigma 0 should be negative. For a stress like this, which means for the non-diagonal part of the stress. For the isotropic part of the stress, we discussed what was the sign of the response, and it has to be positive. So that tells you that if I add a stress, I change the order parameter for the reference value and there is no stress, and I assume linear response theory. So what I want to do now is go back to what I did 3 days ago when I discussed the fluidization of a tissue by cell death and cell division. And I want to show you that if I do the same thing exactly, but for a tissue which has spontaneous nematic order, then it generates what I called an active stress yesterday. So generically, if I have a tissue which has spontaneous nematic order, it behaves as an active material. So that's what I want to show you now. So I remind you what I did last week. I split the stress into two components. So the transverse stress I wrote it as the sum of the elastic stress, so sigma tilde is equal to the elastic component Now the elastic component is the elastic deformation of the cells, and this internal stress was due to cell division and cell death. Now let me remind you what were these two components. This is usual linear elasticity, so sigma elastic alpha beta is 2 mu u tilde alpha beta, where this is a deformation tensor. This is general elasticity, and mu is the shear modulus. The internal part of the stress is due to cell division and cell death. And what I argued was that the absolute value doesn't matter. What matters, because it's due to cell division and cell death, is the change with time. It's only changed when a cell divides or when the cells die. So what I wrote is d sigma alpha beta dt, and I wrote it as minus rho. Then there was a factor kd And my argument was, if I look inside the tissue at a given time and at a given point, there is only one tensor, which is the cell orientation tensor. So this Q alpha beta that I talked about. What I argued 2 days ago was that this Q alpha beta should be proportional to the stress. Of course, I have to change that now. I have to use this relation where the difference from the intrinsic Q alpha beta is proportional to the stress. So I will rewrite that. See that Q alpha beta is sigma so because this is what I had for an isotropic tissue, because the tissue is nematic, I have an extra term here that corresponds to the spontaneous orientation of the tissue. Now if I take the derivative of this one, and I add the two equations. So I write d sigma alpha beta dt, and then I have a term which is 2 mu the time derivative of the deformation is the shear rate tensor, or the velocity gradient tensor. And then I have this term here, minus rho sigma So this term will give me what I had before. It will give me the viscoelasticity of the tissue, which is solid at short time and liquid at long time. So I had introduced the time that I defined as 1 over tau A, which is all of this. So it is rho so I get d sigma tilde. This gives me plus one over tau A sigma alpha beta, which is the viscoelastic relaxation. I have the viscosity term, 2 mu v tilde alpha beta minus sigma 0 over tau A to alpha beta 0. Yes? No. Sigma elastic is the deformation, okay? Then I take the derivative with respect to time, and I get the velocity gradient. So this is what I get, okay? If I take the derivative of that, I get the velocity gradient and on the deformation. So the way I wrote that is I multiply everything by tau. So d sigma So this is what I call the constitutive equation, now for a tissue which has nematic order. So this is what I had before. This is the viscoelastic Maxwell behavior. And then I have an extra stress. Now if you remember what I showed yesterday, the extra stress is proportional to the local order in the tissue. So this looks exactly like an active stress. Now this is exactly what I told you yesterday. The name I gave to sigma 0 yesterday was sigma 0 equals zeta delta mu. So this is just minus q alpha beta. The main point of that is that because of cell division and cell death, in a tissue which is nematic, I generate an active stress. And if I study a tissue which is nematic, I shouldn't use standard hydrodynamics. I should use active hydrodynamics, which means the hydrodynamics that I talked about yesterday for active matter. So that's the main point. A point I didn't make yesterday is that this, whatever you do, is a non-equilibrium effect. So it shows up in my derivation of yesterday because there is delta mu here. So I need to put the ATP reaction out of equilibrium to impose this stress. But there is more to it. There is no way you can derive a stress like this from a free energy. So this is a stress that doesn't come from any free energy and that cannot exist in any active system. And that's an important thing. It has to be non-equilibrium. I mean, a cell is out of equilibrium and a tissue is out of equilibrium. And it shows up here. This is something that wouldn't exist at equilibrium. So what I want to do now is show you effects in tissues that come from this non-equilibrium active stress. And the way I will do it is I will show you experiments. So I will need your help. You're in good shape. So what I will consider is what I call the first-day tissue monolayers. So they are cells which are put on a glass surface. In the beginning, they are far from each other. They divide, they cover more and more of the surface. Then they are confluent, which means they cover the whole surface. And we study them when they are confluent. Now, the first thing I want to do is discuss defects in these pneumatic cell layers. Something went wrong. Sorry, I have to reboot. Okay, so what I want to study is a layer of cell on the surface. These cells, as you will see, will be elongated. They are what my colleague Pascal Silberzan, who does the experiment at Institut Curie with his group, calls spindle-shaped cells. Now, these cells are elongated, and you will see clearly on the pictures that they show order. Nothing a priori tells you whether this is pneumatic or polar order. Now, one way to distinguish between pneumatic and polar order is to look at the topological defects. what I told you yesterday is that in a pneumatic tissue, you should observe +1/2 and -1/2 defects. If a tissue is polar, the only defects you can observe are +1, -1, and integer defects. So here is so here is the picture of the monolayer from above. There is a list of cells here that he has used and which are all elongated. The one which he mostly uses are this one, RPE1, which are retinal cells. Now if you look with a small magnification, this is what you see. And if you magnify, you see that there is this order that appears here, and all the cells are parallel. They are strongly elongated and they are parallel. You see defects of the order. There is one defect here, there is one defect here, and there is one defect here. This defect is what I call the -1/2 defect. This defect is a +1/2 defect, and this defect is a +1/2 defect. So in these cells, you only see half-integer defects, and that imposes that the order is nematic. Now, why is the order nematic? Why aren't these cells polarized and all in the same direction? The idea that I have, but I have no experimental proof, is that of course if you measure the position of the centrosome with respect to the nucleus, that defines a vector, but this switches pretty fast between one orientation and the other one, and on average you see something which is nematic. Who wanted to ask a question? I lost him. No? No question? Yeah, two. Is it known? So they don't have spontaneous motility. That's known. I mean, that's observed in the experiment. They don't seem to have front-back polarity, and if they have it, it inverts faster than the experiments that I will show you. I'll come back. Why don't I expect to have +1/2 defect to polar? Let me go. So here's a +1/2 defect, okay? Suppose I put an arrow in this direction here and make one turn, and the arrow is in the other direction. So there would be a singularity on all the lines, and you know that the defect should be a point defect in 2 dimensions. So these aren't acceptable because the polarity wouldn't be continuous. Yes? But if it's actually polar, it won't do that. It cannot make it because it would point like this here and it will point like this below, and that would give you a singularity line. Yeah. Okay? I'll be back. How is the, or how do we get that? So yes? What is the question? I didn't get what it. Or you increase the resolution and you see that. That's it. Julia. My claim would be that they change their polarity too fast. You will see the time scales that I'm talking about, and they're extremely slow. I mean, we'll have to watch that for days before we see anything interesting. A comment on the comment. That's not true here. So the next slide is to tell you that it's not true. So I have a third figure here. And in this figure, they measured the local velocity of the cells. So there is a scale. And the point that I want to make is the scale of velocity here, which is micrometers per hour. So if you want them to move by 1 micrometer, you have to wait an hour. If you want them to move by something reasonable with respect to the size of the cell, 20, 30 microns, you have to wait for a day. So if you want to see them move, you have to wait for a day. So this is high velocity. This is high velocity, and this is low velocity. And you see that this corresponds to that, this corresponds to that, and this green part corresponds to that, which is consistent with what I said yesterday. The plus half defects move, and the minus one half defects don't move. So the other thing that it tells you is that the system is active. It's active. It moves here because close to the plus half defect, there is a large gradient of orientation of the order parameter, and this is where you expect it to move. So it moves at the plus defects, and it doesn't move at the minus half defects. Now this is again to explain plus half and minus half defects, which I certainly don't need. Now if you take a very broad field, there are many defects. Now what Pascal is saying is that when the cells are not confluent, they grow in various directions. When they become confluent, you freeze a lot of defects, but afterwards, there is no defects which is generated. So the only thing that he sees is defects disappearing, and they disappear by annihilation of plus a half and minus a half defects, but you don't see any creation of defect as long as the cells are confluent. And then you see that a function of time, the number of defects decays. It doesn't decay to 0, so there are defects which remain trapped here. Of course, he didn't go very long, but he waited for 80 hours, which is almost 4 days. And after 4 days, you still have defects that have been trapped and that remain in the layers. There are plus 1/2 and minus 1/2 defects, and there seems to be a fixed number of defects. Then you follow the plus 1/2 defects, which is here, and this is a trajectory of a plus 1/2 defect. Clearly it moves, and if you look in which direction it moves like this, and this tells you that the system is contractile. So the plus 1/2 defects move. What I told you yesterday is that the minus 1/2 defects have no preferred orientation, so they should diffuse. Here is a typical trajectory. This is an experiment. This is not something drawn by me. This one is also an experiment, and this is a trajectory of a minus 1/2 defect. And you see that it travels around, it kind of diffuses, which is what we expect. We don't expect finite velocity for minus 1/2 defects. So qualitatively, this fits pretty well what we expect. The tissue is an active system. It's pneumatic, it's contractile. Plus 1/2 defects move, and minus 1/2 defects don't move or diffuse around. Yes? So the way, I'll tell you what I understand from that. The way they grow the monolayers is they start from cells which are isolated. Then locally, it becomes ordered, but at various places, the order is different, and you generate the defect when these systems become confluent. And it seems that all the defects are created at this point in this experiment. Yes? Why the number of defects is not going to 0? There's this, the real answer is I don't know. There are defects that remain trapped here. Maybe if you wait longer, the number of defects will still decay. I'm not quite sure. It means at this point, annihilation of creation of defects just stops to be efficient. Joker, I don't know about that. I'm sure that they get a finite number. Whether the number is reproducible, the whole story is, as a defect depends on how you start your experiment. Maybe there's some memory for that, but I don't know. I'm sure that there's no experiment where it goes back to 0, and they made several, and they made experiments with the whole series of cells that I showed in the beginning. Yes? Yes? That that reduces annihilation for sure. I don't know, do you have comments on that, Julia, on the simulations? Do you reach a finite number of defects after a long time or not? Yeah, this is why I insisted on that, because I heard you say that, but I asked this question 10 times to Pascal, and I come back and he says, no way. There's never, and so the answer I trust, and I asked it many times. So this is the only thing I can say. Now, the idea of Pascal Silverzan was we have to study these defects, and one way to do that would be to confine them. So what he did, instead of looking at a large field, he made a small circle like this with areas of order hundreds of microns, size of order hundreds of microns, and instead of having cells everywhere, he only has cells on this small area, which is a disk on the surface. So this is the original configuration. And then he waits as a function of time, 15 hours, 30 hours, and even more than that. Now I have a movie to show you. So here you have many defects. It's hard to see anything. But defects disappear, disappear, disappear. And in the end, you have one defect here and one defect here. So you start with many defects. It looks completely disordered. There is annealing in the sense that plus half, minus half, this inclination pairs disappears. And in the end, you have 2 plus 1/2 defect. Now, this is not a surprise. This is not a surprise because if you look at the orientation of the cells on the perimeter here, the cells are parallel to the edge. And if the cells are parallel to the edge, you know that the minimum topological charge you can have inside is +1. So somehow you have to make +1. You can make +1 with 2 plus 1/2 defects. You could make +1 with a +1 defect, but that's not allowed because it's not polar. And then what it means is that if you sum over all these defects, the charge should be +1. So that we expected as long as we let the defects relax, one by one. So a cell is this, and here's just the local orientation. So they draw lines as a function of the local orientation. So it's not anything except so in here, you would draw a line like this one like this, etc., etc. So it's kind of an average, a local average on the cells. Yes?
Have you looked at spatial correlation functions at the order?
No, they haven't. No, they haven't. No, it was the same question? The same answer. So that's just an orientation field. Now I'll play it again. Watch again the time scale. So it goes fast, but several days it takes to do that. 30, 40 hours. 60. It's about 3 days or 3.5 days on which they do these experiments. Yes? So the cells are dividing, can divide, but when it becomes very dense, the number of cell divisions is a bit lower because there is no room for the cells to divide. The other thing you can look at is the velocity field. Now, essentially, there is no velocity field here. So unfortunately, they changed the color code. Red now is low velocity, essentially 0, and the velocity is 0 everywhere. So I argued a minute ago that the system was active, and activity doesn't seem to play any role here. One reason would be that there is friction on the substrate, and that the dissipation to friction is very high, so the velocities, if ever they exist, are extremely small. But there is never any important motion due to activity. So this is the final state. Now you can look at the position of the two defects. They're always aligned with the center in the end, and they're always symmetric with respect to the center. So that's always the finite position that you find. Now, due to the fact that there was no activity, we calculated the position of these two defects in a circle like this for a passive nematics. We decided that activity doesn't play any role. If activity doesn't play any role, you can write the nematic free energy. You impose two defects in a circle. You can do that explicitly. And then you calculate the energy, and you look where the minimum of energy is. So we assumed that the defects were aligned and symmetric, because this is always what we observe in experiment. We also check theoretically that the minimum is when they are aligned. And we plot the energy as a function of the distance of the defects from the center. I insist it's for a passive nematic. So for a passive nematic, the director makes an angle theta, and the energy is just what I call the stiffness yesterday times the gradient of theta squared integrated over all the area. And the energy looks like this. Now there are several curves because of a referee's question who said, but why doesn't the core of the defect play a role? So there is an epsilon here. Epsilon is the size of the core of the defect divided by the size of the disk. And this is how the energy shifts when you change the size of the core of the defect. The minimum is almost always at the same position. We can do an analytical calculation in the case where the core of the defects goes to 0. And what the calculation tells you is that the equilibrium position of the defects is 0.67 times the radius of the disk. So the prediction, if I assume that there is no activity, is that this length is 2/3 of this one. And that fits extremely well the experimental data. So if I assume that there is no activity, because there is no velocity field essentially, the defects is where you expect them for a passive nematic. Is that okay for everybody? They did another thing, is that they looked at the fluctuations of the position of the defect. So you say there's a minimum of the energy, there's noise, so the position of the defects will fluctuate, and there is some kind of effective temperature that characterizes these fluctuations. Experimentally, if you do that, you find an effective temperature with lots of uncertainty, which is the same for all radii. So they change the radii between 400 microns and 800 microns, and the effective temperature doesn't change with this range. So that's kind of a measure of the noise, which in my mind is active noise in these systems. But this is the only effect of activity. So that's what you get from the study of defects, and you know that your system is active and nematic. Now, and without not discussing very much before, what Pascal said, okay, I put them on a circle, why don't I put them on a stripe? So that's what I will call spontaneous flow transition. So same experiment, except that he doesn't put adhesion molecules on a circle, so the cells don't go in a circle, they go on a very long stripe. So this is a cut of the stripe. There are two treatments of the surface here that don't allow the cells to go out, and the cells are very long in this direction. I insist on the fact that they use x as this variable, and they used y yesterday, and they use y as the variable along the stripe. So the velocity is along y, and the velocity will vary along x. The first thing you can do is you can look at the orientation of the cells. On the edge, they are parallel to the edge, which is the same as in a circle. But if you look in the middle, so they took this small square here, you don't see how they did it, but they draw the orientation of the cells here, and the cells are almost at 45 degrees. So what it means is that there is a gradient of orientation of the cells in this direction. If there is a gradient, what I told you yesterday is that there is flow. So you expect that this system is flowing spontaneously. It's almost the same thing as I showed you yesterday, except the boundary conditions are not the same. And a naive guess is that there is no stress on either side. We can do better than that, but that's the most naive guess. So what I will show you now is a picture which is enlarged from this one, and that will show you that the cells flow. So the cells go up in this direction, and they go down in this direction. So you see the velocity, the time scale. You have to look for a few days. And the order of magnitude of the velocity is what I said before, microns per hour, or even fraction of microns per hour. Yes? These are all the same cells from the beginning. They are RPE1 cells. So they were, I wouldn't say they were passive. They were weakly active because we saw defects moving. So, okay, I'll go back to that immediately because I was worried about that. So there's a whole list of cells here. They did the experiments with almost all of these cells. And they see the same effect for all the cells except for one, which means that this one is not active enough to show the flow. That for the minimum stripe, the transition has not occurred yet. So, but for all the other ones, they see the same spontaneous flow appearing. So there is a shear flow. And of course, what I will so you can redo the calculation that I showed yesterday, change the boundary conditions, change them as much as you want. The only thing you do is you change the critical size by a prefactor. So that's extremely simple, and you can do it explicitly for a bunch of boundary conditions. It goes up on this side, and it goes down on this, and in between, it's almost a shear flow. Sorry? No, it's very elongated. What was on the previous picture is a slice that was cut here, and that's extremely elongated in this direction. I don't know how much, but almost millimeters. Oh, what happens at the end? When it's no, it's not closed. It's on a microscope plate, and they stop at the end of the plate. Yes. So I'll show you. So there are two ways to see that. Either you change the activity and you have a critical size depending on activity, or you change the size and you see when it becomes critical. So you can make it quantitative. This is a cell orientation as a function of the width for these RPE cells. If the width is very small, it remains parallel to the substrate, which is 90 degrees. Somewhere here, there starts to be a gradient of orientation, and you see that there is a very strong gradient of orientation in the middle. And you can look at the velocity field. So this is close to the width where you see the flow appearing. It's almost a straight line. It's almost a shear flow. And if you take much wider systems, there is velocity at the edge, and it's flat and no velocity at the center. And here's a quantification of the velocity. This is a shear flow. And then for some stupid reason, they decided to measure the velocity in the transverse direction. So they measured the velocity like this, but they also measured the velocity in the transverse direction. So this is the velocity in the transverse direction. It doesn't seem to depend on the width, and that's rescaled by the width. It's x over L. And it's symmetric with respect to the center, and it's a pretty good straight line in between here. So there are two things that weren't in the theory. There is this fact that the velocity is 0 at the center and appears only at the edge. There is this fact that there is a velocity converging towards the center. And then there's a third thing, which is we looked at this movie many, many times, and there is a chirality which is like this. Now, one day somebody asked, but do they ever rotate in the other direction? And do they rotate 50% of the time in one direction and 50% of the time in the other direction? Victor, who was a postdoc doing the experiments, is a very cautious guy. He said, wait for next week, I'll check that. And the answer is no. Which means if you take this type of cells, it always does that. It never does that. So it means the system somehow is chiral because it selects all the time one orientation and not the other one. Then they did it with other cells. So the next one rotated in the same direction, but there's one of the cells which I showed, I don't know which one, that rotated in the other direction. So it's not an artifact of the experiment. There is chirality in these systems, and chirality is such that it forces one of the rotation angle and not the other one. No. Did they do genetic modification of the cells? No. Pascal was more clever than that. He went in the literature and looked at these, what people say on these RPE1 cells, and there are reports that say that these cells are chiral. I have zero explanation for that. There are all kinds of chiral components in a cell, so that may be enough to make the cell chiral. It's not obvious, though, to start. For instance, actin is chiral. Actin is a plus right-handed helix, and you might say, okay, this is enough. It's not enough because the two types of cells that rotate in both directions have the same actin, and I don't know. But it's reported in the literature that these cells are chiral. Yes? Okay, so I didn't talk about that yesterday, but I found an instability for a mode which is like this, which means the orientation vanishes on the edge and maximum at the center. And then if you go beyond the threshold, you have a mode that does that, and then 3, and then 4, and then 5. I don't know. What I would expect for chirality is at least close to threshold. You should have half of the cell rotating in one direction and half of the cell rotating in the other direction. And that I do not observe. Yes? I'll come back to that. Yes, there is. I'll show you. So this one here is the velocity around y, so along the strips. This is the one I'm talking about. You see that this is again in micrometers per hour. So, and it's this is the one like this. And this one is converging. It's much smaller, but this is the only thing you can say. I'll talk about that in a minute. I mean, you can ask your question later. I'll talk about that in a minute. They hardly see any defects in there. Okay, so there are 3 things which we haven't taken into account, and maybe I'll write them down here. So there is so it's friction of these cells on the substrate which is below. They move with respect to the substrate. Now what this does from a physical point of view is that the divergence of the stress is non-zero. The divergence of the stress is the friction force. So what I wrote yesterday was that dy equals 0. That's not true. There's a friction force that comes from the substrate. So the most naive thing you can imagine, you say this is minus some friction coefficient times the velocity. So the velocity is along x. And then this is what you have to solve and not the equation that I showed you, that I gave you yesterday. Now there are two things that come out. Friction shifts the transition. And you can calculate that. You find that 1 over the critical length squared for a friction coefficient, which is gamma, is 1 over the critical length squared for a friction coefficient, which is 0, minus a length, 1 over lambda squared, where lambda is this is gamma 1, nu 1, over the friction coefficient to the 1/2. Now you see that if the friction becomes equal, if the friction length, which is here, becomes equal to this critical length, this one becomes infinite and the transition disappears. So if the friction coefficient is too large, the transition disappears. Now if you make the friction coefficient equals 0, this length lambda becomes infinite, and you find the result that I had before. If you increase the friction coefficient, this one will decrease, and at some point this one becomes infinite, and that's when there is no more transition. This length, eta, is the viscosity. Gamma 1 is the rotational viscosity, so it's a viscosity divided by a friction constant to the 1/2. Now, friction and permeation more or less play the same role in this equation, so that's the same result that I had. I have a length that compared viscosity and friction. At distances smaller than this length, viscosity dominates. At distances larger than this length, friction dominates. So at distances smaller than lambda, viscosity dominates. This is what you see here. When the dissipation in the system is dominated by viscosity, there is flow. The flow is screened, and in the middle, you are further away from the edge. You are at a distance larger than lambda from the edge, and then the friction is such that there is no flow in there. And you can measure this length here. It's something like 50 microns. And if it's too large, and it didn't go at large enough distances that they saw the transition disappear, they always saw this exponential decay, more or less, of the velocity from the edge. The second effect that I need to talk about is the transverse flow, the question that you were asking. Now, if you want to know more about friction and everything I will talk about, ask Louis or go see his poster. He's done this calculation in great details. So essentially what we see is a velocity that varies linearly with the position that goes from the outside toward the center. Now somebody asked a question about cell division, and one guess that we have, and that we haven't checked in details yet, is that the cells could divide at the edge of the layer and die inside. So what I'm guessing, and I'll show in a minute why I'm guessing that, is that the cells would divide here. When they divide, they have to move inwards, and they die inside. So I'll call Ka so death rate. Now, when I know the death rate, I showed you that I can calculate the velocity from the conservation equation. And I will do the most naive approximation, which is that the system is incompressible. So the conservation of the cell equation becomes divergence of V not equal to 0, because there is cell death. So divergence of D is fixed by the rate of cell death. Divergence of D is minus Ka. Now everything only depends on y, on the transverse coordinate. So the only thing that I have here is dy Vy is equal to minus Ka. And so Vy is minus Ka times y. And if I take this straight line here, the slope is just minus Ka, and this slope would give me the cell death rate. So at least this fits the experiment. The numbers are kind of okay. But if I have a velocity Vy, there is a velocity gradient dy Vy. And as I told you, there is an interplay between the cell orientation and the velocity gradient. If I change the cell orientation, I change the if I change the velocity gradient, because of this new term that I was talking about, I will change the cell orientation. And so there is an interplay of this flow with the transition. So cell division or cell death will change the transition. So we calculated all that, and again, you will see that on Louis' poster. Yes? One reason is I know that if there is a constant death rate, this will be a straight line. Now, there's something else which might be much more interesting than all of that, which is that in some cases, cells don't divide enough, and there are too many cells, and they go in the third direction. So there is a second layer that appears, and this is something that led us to believe that it had to do with cell division and cell death. Yes? I didn't hear you. So turning out, I don't know, but they are trying to make more quantitative the fact that there is a second layer appearing, and we are trying also to think about that and how this second layer should appear. It seems to appear from the edge and move towards the center, which is again an argument that that could be to cell division. There might be biological ways to tune cell division. There are drugs that decrease cell division. They haven't done it yet. Okay? So the third effect is chirality. Wait. It could be. And one of the things that we are currently doing is trying to see what happens if you let cell division and cell death depend on pressure. So that's one of the things we are currently doing. So chirality. If I decide that the cell is chiral, and this is what you read in the biological literature, you have to make an active theory, not for a pneumatic system, but for a chiral system. What I mean by that is that I have the same order parameter, I have the same fluxes and forces, But when I write what I call the transport coefficient matrix, what I showed you is what this matrix is if you impose nematic order. And now I have to do it if I impose chiral order. Now you have to restart the theory from the beginning. There is a new slow variable, which is a rotation. So the matrix, instead of being 3 by 3, becomes 4 by 4. This has been done in a systematic way by Frank Ulischer and one of his students. I won't write the whole theory in its whole glory because it would take half a blackboard. The only thing that I want to show you is a new term that appear for the two equations for the polarization and the stress in the geometry that I'm considering. So the first equation is for the stress, sigma alpha beta chiral. So remember, this is what I call the deviatoric stress. It had a component which was the active stress. It has a component which is a viscous stress. And it has a component which is a coupling of the stress with the orientation. If you make the system chiral, there is an extra term that appears, which is the one that I will show you here, which is minus zeta chiral delta mu epsilon alpha gamma p gamma p beta plus epsilon beta gamma p gamma p alpha. So there is an extra active term which is allowed by the theory, which is this one. Epsilon alpha gamma is a totally anti-symmetric tensor in 2 dimensions. And this should appear where the system is chiral. So you see it here, you see it here. And that's associated to torques. This looks more or less like a torque. So that's the term that appears in the stress equation. There is an equivalent term that appears in the director equation. Which is lambda c p alpha. So big P, remember, is the derivative with respect to time of the director, but it's a co-rotational derivative. So it's d. So in here, there is one term which is a rotational viscosity. There is one term which is a coupling to the stress, the flow alignment term. And there is an extra chiral term, so I will put a C here. And the extra chiral term is lambda C delta mu epsilon alpha gamma p gamma. So this one again is chiral because it has this term, this totally anti-symmetric tensor epsilon alpha gamma. It's active as well. So these are two terms which are active and which will modify the equations that I gave you. This one is kind of a torque around the director. So before I show you what this term do, I'll go back to that. Now, what I described to you is what I called a phase transition, a dynamic phase transition, or bifurcation, whatever you want to call it. Now, the way you want to plot that is you want to plot some kind of order parameter, and the order parameter that we chose is the viscosity on the velocity on the edge as a function of the width of the system. So you see the smallest they did is 20 micron, and they went even beyond that. If the width is too small, if it's smaller than the critical width, the velocity is 0 at the edge, so it's 0 everywhere. And the velocity grows, and it grows close to the critical point as a square root, which is what you expect for a continuous transition or a critical bifurcation. And this would be a fit, assuming that this is a critical bifurcation. So it's like if you want some kind of Ising model in field where this would be the paramagnetic phase and this would be the ferromagnetic phase, except that it's a dynamic phase transition. If you look at these two terms, this one and this one, if you compare to the Ising model, they would act as a field acting on the Ising model. So you know what a field does on the Ising model. It smoothens the transition. So instead of having a sharp kink here, you have a transition which is soft, and that does something like this, avoiding the singularity. So that's what you expect. Now, you would agree with me that it's very difficult to decide whether this is a sharp kink or whether this is a smooth curve that would be very small here and then join this line here. So at least if I look at this curve, I have no way to decide whether these terms are 0 or are small. The only thing you can do is you can put an upper bound, and they're very small, and they don't do anything. However, they break the symmetry. So the output of that is, if I look quantitatively, I hardly see anything, but if I look at a macroscopic scale, because I have this chirality, turning in this direction and turning in this direction is not the same. And when I do the experiment, the system chooses a direction which is favored by chirality. So it's like in a phase separation in an Ising model. If you put a tiny field in the plus direction, when you are in the region where it should order, it always order in the plus direction and never in the minus direction. So that's what you observe here. And the only thing we were able to do is put upper bound on this coefficient and this coefficient. Maybe my last comment on that is that there is another mechanism that you could imagine with a chiral system. If I look at what happens at the edge of the system, I go in the wrong direction. So I look here, and I look on the edge here. On the edge, I have a chiral vector, which describes the chirality of the system, and I have a normal vector, which is a normal to the edge. If I take the cross product of this, one of them is a pseudo vector, the other one is a normal vector. If I take the cross product, so the chirality is like this, the normal is like this, I will get a vector which is like this, which is a normal vector. So having chirality plus an edge can generate a velocity. And if you do it here, if you find a velocity going in this direction, on this side you will find a velocity going in the other direction. And that would perfectly explain the appearance of flow. However, this has no threshold. Whenever I have chirality and a normal vector, just by symmetry, there should be a small velocity on the edge. And the fact that there is no threshold, I think it's clear in the experiment that there is a threshold. So I kind of tend to discard this mechanism. Also, the fact that I find that chirality is extremely small tends to say that this velocity would be extremely small. So we haven't done too much explicit calculations of that, but that seems to be a tiny effect as well. Is that clear to everybody? So that's where we are. So there's a question which might not be relevant for this audience, but which people like Pascal Silberzan or myself would worry about, which is, does this have any biological relevance? I mean, is this just a game for physicists? That's fun. We were extremely happy. We knew about this transition for 10 years. When we did that, we got a mail instantaneously in the evening from Raphaël Voiturier, who was the one who did the theoretical calculation, who said at least 10 years afterwards they show the effect experimentally. But maybe it's just a game. So, not me, Pascal Silberzan, went in the literature and tried to see whether there were things like this that were reported. The thing that he found is that in certain cancer tumors, the cells tend to walk along fibers towards the tumor, and sometimes people report that there is a shear flow. So maybe this is related to that. where the substrate will be the fibers, and there is a band because the fibers have a finite width, and the spontaneous shear flow should appear. I'm not sure that this is exactly what we want, but what they decided is that they should look at that in more details, and maybe sometimes in the future I can tell you more about that. So maybe there is some significant biological relevance of this for the motion of cells towards and away from tumors. And that's the only thing I can say about that. Defects, I forgot to say about that. Same question. Do we care about defects to have fun, which to me is enough, or is there anything about defects? It seems, and there are several reports on that, in particular by Benoît Ladoux in Paris, Université Paris Diderot, that whenever there is a defect, cells are extruded from the monolayer at the defect. So I talked about apoptosis. In cell layers, it's not obvious that the cells are expelled from the layer or whether they die. Depending on the people you talk to, they tell you both. But there are several reports now that tell you that if ever they are expelled, they are extruded from the layer. They do it at defects. So in this sense, it would have some importance to look at the defects. So I'll stop here with this experiment, but in this sense, tissues are a very nice model system for these active pneumatic systems where you can probe things that were never found anywhere else. Now, as Julia was saying, there are now reports on other systems where people have observed. Francesc Sagües, who was here last week, for instance, with his microtubule, observed the same transition. Are there questions on that? Okay. So I want to completely shift gears and tell you about multicellular spheroids. Okay, so I don't know if you remember, but this is one of the first things I showed you. If I can find it back, yes. So the first day, I showed you this picture. These are aggregates of cells. These are cancer cells. You can do them with normal cells, but it's very hard. But with cancer cells, it's kind of trivial. The size is between 200 microns and slightly less than a millimeter. So you start from a small aggregate, you let it grow, it takes 10 days, 20 days, and you reach something like this, which looks like a drop of cells. So essentially what I want to show you is that considering that as a drop of cells in the sense of a liquid drop is kind of a good picture. These correspond to different systems, but mostly to different imaging techniques. In these ones, you see individual cells. Here you see a core, which is different. If you wait too long, 20 days, dead cells accumulate in the center, and you have what people call a necrotic core, which is that. Now, these were invented to test cancer drugs. So you choose the cancer cells that you put in here. You take primary cancer cell lines, and then you can test drugs on that. And they are still considered as one of some of the best systems to study cancer drugs. There is another type of systems now. If I go to the end, I might talk about it, which are called organoids, which might be even better than that. So that's what I want to discuss. Now, the other thing I want to show you is this. So how do you make an organoid? So this is a movie that Fabien Montel, who was a postdoc who was doing experiment, made almost for me. I was asking him question, how do you make them? And he said, next time I do it, I'll make a movie and then I'll show it to you. So this is a Petri dish where you put cells and the cells aggregate and the aggregates merge, and little by little you form these organoids. So you see they merge, they make small bubbles or drops or whatever you want, and then the drops merge, they make larger drops, they divide, you see cell divisions. So they let them grow like this. When they decide they're big enough, they put them in a pit, and then they let them grow only by cell division. So that's how you form these organoids. The thing I wanted to point out is that if you look at the small aggregates that you have, they're always close to spherical. Now, if you look at the first picture that I showed you, these multicellular spheroids are almost spheres all the time. And people noticed that extremely early. And the suggestion made by somebody called Malcolm Steinberg, who was a professor at MIT, is that tissues have a surface tension. I don't quite know. Sometimes they cheat. If you want to make them efficiently, you take a Petri dish which is not flat, but which is a little bit curved so that they go in the center and they meet in the center. Now, you have to, this is why it's only easy to make with cancer cells, because if you try to make them with healthy cells like to grow in 2 dimensions. In order to make 3 dimensions, you have to detach from the layer and go make on top, make another layer, and they tend to die when they do that. This is a phenomenon which is called anoikis. It's doable. People in tissue technologies or biotechnology found ways to make cell aggregates like this with healthy cells, but it's difficult, too difficult for physicists. Essentially, with certain cancer cells, they always do that. And I'll show you a bunch of them afterwards. But there is some trick in the preparation that you have to start the aggregate. And cancer cells don't die enough, as you know. And so it's much easier to do with cancer cells. That's all I know. But your question is relevant, I agree. Ricard.
How do they move in one?
What's the time scale of that? I don't know. I forgot. I'm sorry, I forgot. They jiggle around. They probably have some, maybe they have some spontaneous motility, which is randomly oriented or something like this. That's the only thing I could say. I know what they are. They are mice colon cancer cells, because this is the system that we mostly study in the physics department in Curie. Okay, so what Steinberg was doing, he was working in development and he was extracting cells from developing animals, and he always had these stuff that looked like spheres. And he had a very nice way to do it, which I will completely skip. His idea was that there was something like a surface tension on a spheroid. He was a very nice guy and very much liking to do experiments. So the first thing he did is he tried to devise a way to measure this surface tension. Now, if you, like me, like you worked on wetting when we were young. There are dozens of ways to measure surface tensions. Many of them you cannot apply to cells. So the device he used in the end, and that people have been using almost all over the place since then, is something like this. You prepare your spheroid, you sandwich it between 2 plates, then you apply a force, you measure the height, you measure the radius of curvature, and then I let you do the geometry, but out of that you measure the surface tension. It's not very precise. It's not very precise because it depends on the contact angle, which is here. So the better you fit the shape of that, including the contact angle, the better results you get for the surface tension. Now the numbers that he got, and he did it for dozens of tissues, the result that you get is always that the surface tension, call it gamma, is 1. So the unit of surface tension is newtons per meter, And everybody uses millinewtons per meter because people are old, and in CGS unit, it's like a dyne per centimeter. So it's 10 to the minus 3. And now I don't know how much you know about surface tension. What's the surface tension of water with air? Who knows about that? 72 at 25 degrees or 71 point something. It's a pain in the neck to measure because you want to avoid any impurities. I did that when I was a student. I found 25, which is not very good, but many of us found the same thing, which meant that the surface of water was not water, but all kind of stuff that was floating around. So that's 100 times smaller than the surface tension of water. Then, of course, Steinberg again started to worry on why there would be a surface tension. Now, there is a naive idea, which is to explain this surface tension of a tissue like people in the very old days were doing, like Young and Laplace. So it's 1805 or 1806. The way they were describing surface tension is they were saying there are attractions between molecules, and if you take a material, you cut it into two pieces, you break the links of the attraction that the molecules on one side had with the molecules on the other side. And if you know the interaction potential, you can calculate the surface tension out of that, and the order of magnitude is okay. Not for water because the interaction is complicated. But the idea is that when you put a molecule on the surface, so if you have a molecule in the bulk of the spheroid, it attracts its neighbors. If you have a cell in a spheroid, there are adhesion molecules that are equivalent to attractions between neighboring cells. You put it on the surface, it has less neighbors, so it has less attraction, and that costs energy, and this is the surface tension. So it costs energy to put a cell on the surface. So this was the first idea of Steinberg. And so you know about, I mean, I don't know if you know, but biologists know about adhesion molecules. And the molecules, in most cases, that make adherence between cells are called cadherins. So you can play genetically with the cadherins. You can change the cadherin, making them less adhering or more adhering. And it's partly true. If you do that, you change the surface tension, but you don't have all of it. Now, what Steinberg figured out is that there is another thing which is important, which is what they call the actomyosin cortex. So I want to explain to you what the actomyosin cortex is. You know, and if I don't explain it clearly enough, please ask questions. In a cell, what makes the elasticity of the cell is what people call filament, which are polymer-like protein made by aggregation of some small proteins. And the most important one for cell elasticity is what's called actin. And actin forms what's called the cytoskeleton. Now, actin interacts with molecular motors. The molecular motors which interact with actin are called myosin. If you consider in vitro systems with only actin, it's like a gel in the sense of physical chemistry, so you can use classical physical chemistry to study it. If you add myosin, they bind to actin, they make aggregates and bind to several filaments, and they make the gel contractile. So by the cytoskeleton made of actin and myosins is an active gel. in the sense that it consumes energy. It consumes energy via the molecular motors. Now, actin is a rigid filament, so there is local orientational order. It seems to be more nematic than polar, although the actin filament have the polarity. The polarity doesn't seem to count. But this is an example of active matter. This is even the first one that we ever studied. And the whole theory that I sketched yesterday was made for that in the beginning and not for cells. Now, in cells, you find actin inside what's called the cytoplasm, which is the inside of the cell. But you also find actin close to the membrane. So this is what I want to show you here. So this is optical microscopy images of the edge of a cell. What's red here is the membrane, and what's green is not actin, but it's myosin, because for them it was easier to label myosin. But you see that close to the membrane, there is a layer of myosins, and this layer of myosin wouldn't aggregate there like this, means that there's a layer of actin. So there is a layer of actin and myosin, so a layer of active material, which is close to the membrane, and this is called the cortical actin layer. Now, of course, I'm simplifying these things as much as I can. So I'm talking only about actin and myosins, but they interact with a whole bunch of things. If you want to make it a gel, you need molecules to cross-link actin, for instance. So they bind actin filaments. And there are also molecules that bind this actin-myosin gel towards the membrane. So that's what you see here. It's attached to the membrane. Sometimes the membrane detaches from this actin layer, and you make this big protrusion, which are called blebs, which in the beginning were associated to cells dying, but nowadays are associated to all kind of process. Essentially, what the bleb allows to is relax the pressure inside the cell. So it makes a bleb like this. The bleb lasts so it detaches, actin tends to depolymerize, and then you make another actin layer in the bleb, and that heals the bleb, and the cell becomes flat again, and then it makes another bleb at another place, and things like this. So this is what you see here. Actin is contractile, so it tends to contract like this, so that creates a tension in the cell. Now, what people call the cell tension is the tension of both the membrane plus the actomyosin layer, which is here. And in fact, the membrane is almost negligible. It's 100 times smaller tension than the actomyosin layer. So if you want to see the cell as a ball with a tension, what provides the tension is this cortical layer that I'm talking about. This one here is electron microscopy. People managed to make 3D electron microscopy at the edge of the cell. So the membrane is here. This red stuff is the actin filaments, and the myosin motors are in green. So there is a direct image. This was done in the group of somebody called Baumeister, who is in Munich, who masters extremely well all these techniques and makes this spectacular picture. But this is the layers I'm talking about, which is made of actin and myosin. Now, there are all kind of debates on whether the myosins are everywhere or whether they're only in the back of the layer. I don't want to go into these details. The only thing I want to insist on, first of all, the thickness of the layer is slightly smaller than 1 micron. It's 500 nanometers, maybe 300 nanometers. Everybody sometimes makes a new experiment, it decreases. But so it's smaller than that. There are motors in this layer, and the motors create a tension, and this tension is the tension of the cell. This layer can become unstable, and if the layer becomes unstable, the shape of the cell starts to fluctuate or to oscillate in a weird way. But much of cell mechanics is due to this cortical layer of actin, which is close to the membrane of the cell. Should I stop here, Julien? Wait, I'll stop here, and I'll tell you a little bit more on what governs this tension in the cell.